I told the admin this morning, I walked into the office and I said, I have to grade these exams, and I'm going to shut my door, and unless somebody's on fire, like, leave me alone. Got interrupted 4 times. So we're going to try it again this afternoon. I swear that I'm about I've already got problems 1 and 2 graded. Again, the class is doing fine. Average on problem 2 is like a 91. You know what I mean? So I'm not worried about it. The class is going to do fine. I just need to do it. But I definitely want to do it before Monday because I'm going to have a whole stack of stuff to grade with your submittal. So speaking of, I do want to talk about that. I had given you a checklist of things before. I did add one thing to it. I don't really think it's a big deal for anybody that's already submitted, but I know that a lot of you are going to be working on your submittal between now and Monday. So I want you to know what I am looking for each of your trusses. So if you remember for submittal 1, you need to submit 3 trusses, and then from those trusses, you need to select one and tell me why. Okay? So for each truss, okay, this is what I'm looking for. Number 1, did you show the dimensions? Okay? Did you fully dimension your schematic? I'm looking for the dimensions. All right? Number 2, fits inside the vertical envelope. Okay? If you remember, so there's the there's a support, and there's a support, and I told you that the truss has to fit within these bounds, and I said that it was that this dimension right here was called alpha, and that's on the handout. Okay, so the truss has to fit within that bound. Okay. Number 3, does each individual member length is it less than L max? So, like, for example, you might say something like, okay, so let's say alpha is 15 feet, which I think it actually is for this year, okay? So if you have a truss member that looks like this, right, let's say we're looking at, like, this part of the truss, and here's this, and we're looking at, like, this diagonal. And this dimension here is, we'll call it 18 feet. And this dimension here is 15 feet, right? And you say, well, this is less than 20 feet, this is less than 20 feet, that's good. Well, what's the length of this member right here? It's probably more than 20 feet, okay? So each individual member length has to be less than 20 feet, okay? This one's new. I don't think it's a big deal, but I just want to make sure that for every truss that you submit, that you're checking that there is a joint at the bottom of the truss at midspan, okay? We have to have a joint at the bottom at midspan because that is where we are going to, in submittal 2, check deflections. So if you don't have a joint at the bottom at midspan on your selected truss, you need to look at that. And finally, did you compute IT for each truss, and did IT equal 0 for each truss? That's got to be the case in order for the calculations in submittal 2 to make sense. Yes, sir?
Is there a minimum height?
There a minimum height? No. There's a maximum height, but not a minimum height. But let me also say something. If you have a truss that's 1 foot tall, go ahead. You're going to have some big members in that truss. I mean it. I mentioned, I think, in the my suggestions for your truss that depth equals stiffness. The deeper the truss is, the stiffer it is. Okay? So if you have a really, really shallow truss, you're probably using some really, really big elements. So if you have a truss that's 5 foot tall, 6 foot tall, you're going to use really big W12s on that. Whereas if you have a truss that's 12, 13, 14, 15 feet tall, the W12s are going to be a lot smaller. Okay? So it's not no, it's just, that might happen. Now, I want to be clear, if we get to submittal 2 and you're literally not able to make it work because, between submittal 1 and submittal 2, I don't have a problem if you have to tweak things, make the truss a little bit taller and whatnot, but just be aware that that might happen. Everybody good with that? All right, so submittal 1's due Monday. Okay, today what we're going to do is finish out shear and moment diagrams. We're still going to be using shear and moment diagrams when we do displacements and whatnot, but this is going to be our last discussion on it, okay? formally. So, oh, did everybody get the code? I'm gonna take that as yes. Okay. So I have two sort of topics I want to get through today. So I'm not going to go super fast or anything, but I do kind of want to make sure that we've covered these. And that is to cover shear and moment diagrams for frames, and to discuss what I'm calling structural analysis aids. And those are tools that are going to be very, very popular in courses like steel design or concrete design or timber design, okay? Because it's basically a means of simplifying routine structural analysis, okay? We're still using the same relationships, still the same conclusions, okay? So how do shear and moment diagrams differ for frames? Well, they really don't, okay? The only thing that happens is, so for example, if you're looking at an element that's vertical, you're just drawing the shear diagram vertically and drawing the moment diagram vertically. So for example, if I'm looking at member AB, I just draw the shear diagram like this, draw the moment diagram like this. I'm just drawing it up and down as opposed to left to right. So it's really not that different, okay? The only thing that I might do is I think at the very beginning when we started doing shear and moment diagrams, I started drawing those little tick marks on the horizontal axis. I'm going to do that today for frames just to show which way that we're drawing them. In this, if we're talking about our column, we're going to draw it from the bottom up and whatnot. But other than that, it's pretty straightforward. Sometimes you might want to investigate the equilibrium at a joint to make sure that all the moments balance. You'll understand what I mean when we get to this example here in a bit. For simple frames, it's usually not too big of a deal. And in order to, again, I think structural analysis is a science that you learn by doing. So let's just do a frame problem, okay? So the first thing I wanted to show you is let me go ahead and open up the notebook here. So for this problem, I've given you the support reactions. So we have 60 kips going to the right, so that means this horizontal reaction is 60 kips to the left. And then we have 75 kips going down. This ends up being 30 up and 45 up, just to balance moments. I am hoping at this point that I can give you these reactions and you believe me, and that also that you could compute these support reactions yourselves. I mean, if you sum moments at A, you've got 60 times 10 plus 75 times 10 has to equal something times 30. That something is 45, right? Some forces in the vertical direction. If I've got 75 going down, 45 going up, I need another 30 going up. But that's it, right? So I'm hoping that's pretty straightforward. All right? So what we're going to do is we're going to draw the shear and moment diagrams for what I'm going to call the column and the beam. So the column will be member AB, and the beam will be member BC. Okay? Now, in order to do that, essentially what I'm doing is I'm breaking this member up into two pieces. Okay? And whenever you think that, you sort of are breaking out the secret weapon of structural engineering, which is the samurai sword or lightsaber if you're a sci-fi fan. So essentially what I'm doing is I'm cutting a section like right here, okay? Keep in mind, like I draw the structure with this sort of like blocky depth, like it's got a little bit of depth here and a little bit of depth here, but really analytically we're just treating this as a line, right? So really all this is a line, this, a load, and a roller, and I'm just cutting it right there, okay? So I'm just cutting the line right here. So I'm going to samurai sword or lightsaber through the structure right here, okay? And I'm going to investigate equilibrium at that location, and then I'm going to use those internal forces to construct the shear and moment diagram. And I think you'll find this is pretty straightforward. Okay, so let's go ahead and get into this. And come on, here we go. So we're going to start with the column first, so we'll call this member AB. Okay. So what does member AB look like? It's a 20-foot long member. Okay. It has a 60 kip load, this vertical reaction here, and some unknowns right there. Okay. So let's see what we got going on right there. All right. So Got this. Got that. I'm going to lower this just a little bit. Okay, so we have a load like this. Bless you. This is 60 kips. And then we were also provided a reaction right there, 60 kips. That's AX. I'm drawing that in red because when I'm cutting the section, I sort of know what that is right now. And we have a vertical reaction right here. That's AY equals, and this was 30 kips. Okay. For dimensions, we know that this is 10 feet. We know that this is 10 feet. Okay. So what I'm interested in is to sort of figure out what's going on right here. I mean, let me ask you a question. I want to just look at this structure. Look at this. Is this in equilibrium right now? Just look at that. Is that in equilibrium? No, it's not. Because, for example, I have 30 kips going up. That has to be balanced by something. Otherwise, this is just going to shoot into space, right? So it's not in equilibrium. So what's going on? Well, it's the same thing that's going on when we cut a section with beams. If I'm sitting on this beam, okay, and Mr. Fry takes out the lightsaber and cuts through the table right here, I'm falling to the ground, okay? Because the table right here was containing internal forces that kept the structure in equilibrium. Let's figure out what those are, okay? So how do we do that? We use equations of statics, okay? So let's go through each one at a time. All right. Now this one's easy, okay? So let's sum forces in the x direction. Is there a necessary horizontal force right here to keep the structure in equilibrium? And if so, how much is it? And I'm just talking about horizontal forces. What is this? 60 to the left. What is this? 60 to the right. So if I'm talking about horizontal force equilibrium, if I've got 60 kips going to the left, 60 kips going to the right, what's my unknown horizontal force right here? 0. Okay? So I'm going to call this Bx as 0. And I'm calling it Bx because this is point A, this is point B. Okay? Now what about summing forces in the y direction? What is the vertical, is there a necessary vertical force at B to achieve equilibrium? What is it? 30 what? 30 kips.
Down.
Down. It's got to be down, right? Because this is 30 kips up, we got to have 30 kips going downward. Okay? So, that means that member has to have, so we're close. That's going to keep the structure in equilibrium, okay, vertically, okay? So is this column, by the way, is it experiencing compression or tension? Compression. It's in compression. The column's being squished, right? I mean, it's a column. That's probably going to happen, okay? Now, I've only used 2 equations of equilibrium. I'm missing one, aren't I? That's the sum of the moments, right? So I'm going to sum moments. I'm going to sum moments at point B, okay? All right, let's just think this through. I'm summing moments at B. Does BY generate moment? It's going right through B. It doesn't generate moment. Does AY generate moment at B? No. Does AX generate moment at B? Yes. It's going to go like this. 60 times what?
20.
20. This one's going to be 60 times 10 in the opposite direction, right? So I'm going to have 60 times 20 and 60 times 10. Now, are there any other forces on the free body diagram that I've missed? I took account of this, took account of this, don't need to worry about that, don't need to worry about this. That's it, right? So I'm asking you, we know the structure's in horizontal equilibrium, we know it's in vertical equilibrium. Is it in moment equilibrium right now? No, these aren't balanced, right? I need a little bit more over here, don't I? I need some internal moment right here. So I need something like that. It's almost like it's a cantilever, right? And there's some internal concentrated moment right there that I need to contain, okay? So 60 times 20 is 1,200. 60 times 10 is 600. MB. That means that MB is like that. All right, does that make sense? Not bad, right? Okay. So are we ready to start drawing a shear diagram and moment diagram? Yeah. We figured out all the forces on the system because we now have a set of forces that make this system in equilibrium. Now, how am I going to draw the shear and moment diagram? I'm going to draw it the same way I would a beam. Now, imagine that, see how I've got from A to B? Imagine if I did that. And if I did that, I put the shear diagram here, the moment diagram here. So all I'm going to do is I'm going to put the shear diagram right here, moment diagram right there. That's all I'm going to do. So, let's do that. So let's put my shear diagram right there. Put my moment diagram right there. So we'll call this V. Call this moment. Okay. Now, something I had started doing at the beginning of this that I sort of been skipping because for beams it really didn't matter is I'm going to do this. For beams, wasn't really a big deal to put those little tick marks there, but I'm putting them here for the column because I want to illustrate that when we're drawing this shear diagram, we are starting at the bottom and working our way up. And I want to say something about this after we're done with this example. Okay? So, how does a shear diagram work? We start at 0 and we should be ending at 0. So, I want you to think of it kind of like this. Think about it like we've rotated the coordinate system. So, like essentially what's going on is, like think of it, this is our x-axis and our y-axis is like that. So, you know, you're sort of thinking that like this is x and this is y, so this is me just turning it, okay? So that means that positive shears would go this way, negative shears would go that way. Does that make sense? So, let's think this through. Okay, remember, what is a shear? A shear is a transverse force. So if the member goes like that, shears are perpendicular. Okay? So my question, does this 30 kips right here, does this matter at all when we're looking at the shear diagram for this column? No, it's axial. The 60 kip matters. So what's my, can somebody tell me what the shear diagram is going to look like?
We'll go to the left 60, and then straight line is going to come back by 60 to the right.
That's exactly right. So it's going to go over, up, over. That's the shear diagram. That's it. Now, okay. Let me ask you a question since you answered that. I'm going to ask you another one, okay? I'm drawing the shear diagram assuming that I'm starting at the bottom, working my way up. I want to ask you a question. What if I started at the top and worked my way down? What would happen to the shear diagram? What would it look like?
Probably the inverse of it.
You would flip it. Exactly right. You would go over, 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 right? Now, you're exactly right. Now let me sort of respond to that. Which one's right? Well, they sort of both are, okay? And let me explain what I'm getting at, okay? Later on, we're going to start doing software analyses of structures. So we're going to use software to build trusses, to build beams, to build frames, and have the software plot shear and moment diagrams, okay? Now, what a software program will do, the software program doesn't know which direction we should be doing, okay? So what the software program will do is it adopts a standard routine. It will draw shear diagrams and moment diagrams from lower numbered joints to higher numbered joints. So we don't have letters for joints in software packages. We don't have joint A, joint B, joint C. We have joint 1, joint 2, joint 3, joint 4. So it will always plot from a lower number joint to a higher number joint. So for example, if you're reviewing the software analysis for this frame and the shear diagram looks flipped, well, it might be flipped if this is joint 1 and this is joint 2 because it's going that way. Does that make sense? So that's why I'm drawing these arrows, because with these arrows, this is the correct answer. Without these arrows, it could be this or it could be flipped. It depends on which way you drew it. Okay, does that make sense to everybody? We'll talk about that later when we start doing software analyses. Okay, same idea, we integrate. Okay, so 60 times 10 plus 600. So if we start at 0 for our moment diagram, can somebody else other than you tell me, because you already called on you, what does the moment diagram look like? What's it look like from here to halfway up?
Would it go diagonal out?
Diagonal, yes. Right or left? That is a good question. That's why I asked it. Go left. Because this is positive, so it's going to go up positive. It's going to go up positive. Then what's it going to look like from here to here? Straight line up. And then this 600-foot kip moment is going to bring us back down. Right? So that's what the moment diagram is going to look like. Oop. And then there's that. And that's your moment diagram. Okay? Does that make sense? All right. Now, for the beam, I am going to handle the beam totally independently. I'm going to do the beam as if I never looked at the column. Okay? But we're going to see something kind of nifty. Okay? Does everybody have this? Okay, we're doing good on time. Okay. So let's look at the beam. Okay, so what does the beam look like? It looks like this. Why does it continue to want to put arrows there? We knew this reaction, I think that reaction was 45. We have a vertical force right here, which was 75, right? I believe this was 20 feet. This was 10 feet. I asked you the same question I asked last time. Is this structure in equilibrium right now? No. There are forces inside here keeping it in equilibrium. This is point B, this is point C. Let's figure those out. And by the way, when we did this, so what happened when we did this for the column? So we did this for the column. We got some forces. Now we're doing it for the beam. Getting some forces. What did we get for the column? We got 30 kips down, and we got 600 foot kips. Is that what we got? Okay. Let's see what happens here. Are there any horizontal forces? So Bx is 0. Are there any necessary vertical forces at B? How much?
30 kips up.
30 kips up. Interesting. So you're telling me this is 30 kips up? So 30 down, 30 up. It's almost like we cut a section and regardless of which direction we look, we should get the same magnitude but opposite directions. Interesting. It would be just like, now hold on, do I have a typo here? I do, this is a typo, that's supposed to be like that. Somebody caught me. Now you know what would be wild though? What would be wild is if this is 600. That would just be wild, wouldn't it? That'd be nuts. Let's see if that happens. So, if I sum moments at B, what do I have? I have 75 times 10. And then I've got 45 times 30, right? Right? Now 45 times 30, that's what, like 1350? This is 750. I need a little bit more moment on this side. Because MB plus 750 foot kips equals 1350. It's almost like MB has to equal 600 foot kips that way. That's just nuts, isn't it? That's just crazy. Look what's happening when we cut the section. We get equal magnitudes in opposite directions. So I propose joint B is in equilibrium. So looking at each joint independent, or each member independently, we can go back to the joint and go, is the joint in equilibrium? Well, yes, 30 down, 30 up, 600 this way, 600 that way. The joint's in equilibrium. That's what I meant when I said, is the joint in equilibrium? So, as for constructing the shear and moment diagrams, I'm hoping this is a basic enterprise. Is it okay that I did that kind of quickly? Just up 30, over, down, over, up. Right? So this is, if I integrate this, this is positive 300. This is negative 900. So for the construction of the moment diagram, let me lower that a little bit. We've got to have a sudden jump right here. Linear increase. Back down to 0. Up. I mean, I did that really quickly, but I mean, is that challenging? Okay. All right. Are there any questions on this? Is that simple? Okay. All right. Now with that, I have one other topic related to shear and moment diagrams, related to a little bit of a lie I've been sneaking into my lectures for the past 6 or 7 lectures. But any questions on this? All right. Let's talk about the lie I've been sort of discussing indirectly for the past 7 lectures. Oh, I skipped too far ahead. So let's talk about what I'll call aids for structural analysis. And what I'm getting at is that there are tools to make the construction of shear and moment diagrams a lot easier than what we've been doing together. Okay? So let me explain. This slide right here contains beams that we have analyzed together. Okay? And I expect you in this course to be able to do this. I also expect practicing structural engineers to be able to analyze these beams. Okay? I've mentioned before this whole concept of weight training, right? Think of these as like you pushing yourself in the gym in terms of these are the most challenging types of problems that you would ever need to deal with. However, these are not bread and butter structural analysis problems. Okay? I cannot find a structural engineer practicing today that routinely designs beams like this. That's not a routine problem. These are routine problems, okay? Basic structures, okay? And here's my question to you. Let's take a look at these 2 problems. I have 2 problems here on the screen. This is a 3 kips per foot beam that's 25 foot long, or a 25 foot long beam subjected to 3 kips per foot. This is a 37 foot long beam subjected to 1.95 kips per foot. What I'm asking you is, are these really just different problems? Not really. Really the only difference is the numerical inputs. But at the end of the day, they're both cantilevered beams. They're both subjected to uniformly distributed loads. In that regard, they're exactly the same. So my question is, can't we develop some formulas that we could use to aid these routine analyses, these routine computations? Yes. Okay? This is such an example of that. By the way, this comes from Design Aid 6 from the American Wood Council. So this is an aid that you could download today off the web. But this is a design aid for the use in structural design. There are similar ones in the steel manual, similar ones put out by PCI and what have you. But essentially what this is if I have a cantilever beam subjected to a uniformly distributed load, this is what the shear diagram looks like. This is what the moment diagram looks like. This is a formula for M max. This is a formula for M as a function of X. This is a formula for shear as a function of X. Okay? Plug and chug, the problem's done. Okay? And for routine basic problems, you can find these off the Google box right now. Okay? They're widely available. Okay? And so I do think you should be familiar with them. Okay? Now, I do think you need to be careful when using them, okay? So I don't want you to just surrender to what's already been derived. A good example, so this comes from the steel manual. This is the aid that's been presented for a simply supported beam with a triangular load. But you got to be really careful because they use this term W in the formula, and W is not this number. W is the area of this triangle. So if you just use W, you're going to get the wrong value, okay? So in this case, W is not 2.5 kips per foot, it's 1/2 base times height, okay? Now if you use that, you can plug and chug and get your shear as a function of X, your M as a function of X, even deflections, which we'll talk about later. But you can get all this derived for you. And doesn't this look like the problem we already did? So imagine instead of deriving a formula for this beam, we now have a formula for any beam. Any beam subjected to any load that's of any length. Okay? Very handy for spreadsheets. Okay? Another thing you have to be careful about is when you mix formulas together. So let's take a look at this beam. Okay? Now you're not going to find a formula for this beam. But what you will find is a formula for that beam and a formula for that beam. Okay? So in other words, I'll say that this beam equals this beam plus that beam. The problem is that there'll be an expression for M max. The M max for this beam is WL squared over 8, and it occurs at midspan. The M max for this beam is PAB over L. This is A, this is B, and L is 40 feet. But this M max occurs where the point load is. So the two M maxes occur at different locations. So you can't just add them up, okay? Instead, what you could do is like plot the M of X for beam 1, the M of X for beam 2 in Excel, just sum the columns up, and then plot it to determine M max. Or you could sum the two equations up and differentiate. That works too. I want to show you how we derive these things, and the homework assignment I'm giving you one to derive, but this is really, really basic, but it's so important, okay? So I'm giving you a cantilevered beam. Oh, hold on. There we go. So I'm giving you a cantilevered beam, and what I'm interested in finding are some formulas to determine what are the reactions, what are shear as a function of X, and moment as a function of X, and then what are the M max and shear and V max terms, so that for any beam that's of any length subjected to any distributed load, we can plug and chug. Okay? This is really basic. Okay? So let me kind of show you how this works. Okay? This is a cantilevered beam. It's a fixed support. How many unknown reactions do we have at a fixed support? Okay, 3. What's the horizontal reaction going to be? 0. There are no horizontal loads, right? So really all we're going to have is a vertical reaction, which we'll call RV, and a moment reaction, which I will call RM. Okay? Now, how do I solve for those reactions? Folks, it's no different than the problems we've been doing before. What do I do with this distributed load? I collapse it into a point load. What is the magnitude of that point load?
W times L.
WL. How far do I place that load from here?
L over 2.
L over 2. Okay? So, if I sum forces in the y direction, I have, what do I have going up? My reaction here, my force going down. Therefore, this reaction is WL upwards. So whatever the length is, whatever the distributed load is, plug and chug. Pretty simple, right? Okay. What about summing moments? Let's sum them at the support. Okay. Does RV generate any moment? Does RM generate moment? Well, yeah, it goes over here. What about this? How do I account for this? Does it generate moment? Yeah, so what's the force? WL. What's the moment arm? L over 2. So, a little bit of algebra. WL times L over 2 tells me that this is WL squared over 2, like that. Plug and chug. Never have to figure it out again. Never have to apply statics to solve those reactions ever again in my life. It's done. That's kind of the idea. How do we plot our shear diagram in this case? Here, let's scooch this over. Actually, there are no units. It's just shear. So we start at 0. What does the shear diagram look like for this beam? Is it a stair step? Is it curve? What does it look like?
You would go down diagonally until you get to RV and then go back up to 0.
Exactly. So we'll say negative WL. That brings me back up to 0. How do we construct the moment diagram? We integrate the shear diagram. What is the area of this triangle? 1/2 base times height. And it's negative. Right? Just doing it with letters instead of numbers. It's no different, you know, same idea. And by the way, what is the slope of this line? Minus W. Somebody tell me what the moment diagram looks like.
It curves like this.
It's a quadratic, and it goes, whoo, and it drops down to minus WL squared over 2, brings back up, right? So, in this case, we'll call V max minus WL because I'm really interested in just magnitudes for the purposes of design. What's the biggest magnitude moment? And this is minus WL squared over 2. Biggest magnitude I see here, biggest magnitude I see here. Now, how do I get shears or moments as a function of x? Well, break out the samurai sword or lightsaber if I'm a sci-fi fan. Let's cut ourselves a little section through the beam. Let's cut a section. Which way do you want to look, left or right?
Right.
Right? Well, we can look right, but we have to deal with these. We don't have to deal with these if we look left.
There's nothing to do with them there.
Well, there's this. There's the distributed load. Go with me on faith for a little bit. Go with me on faith. All right? So if I cut a section, this is my unknown shear, that's my unknown moment, right? Some distributed load W, and how long is this segment? X. So if I were to collapse that into a point load, what would the magnitude of the point load be?
W times X.
Times a moment arm of X over 2. Does everybody see that? So, if I sum forces in the y direction, I have V going down, WX going down. So 0 equals V plus WX, which means V equals WX. Sorry, negative WX. So if I sum moments at the cut, I get, what do I have? I have M going this way, and I have WX times X over 2 going that way, right? WX times X over 2. So I get 0 plus W over 2X squared, so M, I get that. Huh. Interesting. One note, by the way. If I differentiate this, I pull out the constant. What's the derivative of x squared?
2X.
2x. So 2's cancel. Then I get my shear. Look at the expressions. Look at the expressions. This is a line. This is a quadratic. Negative slope on the line. The shear diagram goes down. Negative parabola. Parabola opens downward. It's really like it's just a formality really that we're doing this problem together because it's just the same thing we've been doing, just with letters instead of numbers. You now have earned a 2-day break from your structures professor and your materials professor. Get on out of here. I'll pull up the code again. That's all I got, everybody. I'll see you on Monday.